Welcome to the deep dive, where we unpack complex ideas and really try to get to the core nuggets of knowledge. Today, we're plunging into a really fascinating area. It's where machine learning meets the intricate, sometimes, well, unpredictable dance of real-world systems. You know how our world is constantly shifting, right? Think about climate changes or how species interact. A lot of systems change kind of slowly, gradually, but then sometimes bam, they hit a sudden tipping point, a regime shift, and their behavior just fundamentally alters, like ocean currents suddenly changing course or CO2 levels hitting a point of no return. Understanding these shifts is obviously crucial, but trying to model them with simple equations, it often falls short because, well, we often don't know all the underlying processes. We're missing pieces.
Yeah, and that's exactly where things are getting exciting now. Science is really turning to machine learning to fill in those specific gaps. We're looking at a pretty groundbreaking approach, actually, that helps discover those missing terms in the equations, especially when systems get near those critical tipping points.
Okay, so our mission today then is to explore a recent paper. It refines this powerful tool called Universal Differential Equations, UDEs for short, and it focuses on something critical but maybe often overlooked, how we actually grade the AI while it's learning, how we score its performance. And this is where it gets really interesting, because the paper shows the wrong grading method can actually send the AI spiraling into what they call a black hole of loss. It completely misses the true behavior, the really crucial dynamics of the system. So yeah, let's unpack this. So we're talking about dynamical systems. Can you maybe paint a clearer picture? What are they and why are they so tricky to model when we don't have all the info?
Sure. Dynamical systems, fundamentally, just describe how things change over time. Could be anything, really. From the microscopic world, like chemical reactions or biological processes, all the way up to, the vast scales of climate or whole ecosystems. You can sort of map their behavior as paths or trajectories, moving through what we call a state space. Think of it like a multidimensional map. Every single point on that map represents a possible state of the system. But yeah, the challenge pops up when our understanding of what's driving the change is incomplete. We have those missing terms in our equations, and that makes accurate prediction, especially of those sudden shifts, incredibly difficult. It's a bit like trying to predict where a car will end up if you only know its starting speed, but nothing about, say, the driver hitting the brakes or turning the wheel.
That's a great analogy.
Yeah.
Right, and this is exactly where these universal differential equations, the UDEs, come into play. They cleverly combine the power of machine learning with the parts of the physics or the system that we do understand. They learn these missing pieces directly from the data we observe. It's like having a half-finished jigsaw puzzle and using AI not just to guess the missing shapes, but to actually figure them out based on how the known pieces fit together.
Exactly so, yeah. UDEs generally describe a system's dynamics with two parts: a known part, maybe based on physics, and an unknown, machine learnable part. And this unknown component is often represented by a neural network, which is fantastic. I mean, really powerful for approximating complex functions just from data. But the catch is, the neural network often acts like a black box. It can show us the behavior, sure, but it doesn't directly tell us the simple, maybe algebraic form of those missing relationships, at least not immediately.
Okay, so the UDE is trying to estimate the system's behavior, like a student taking a test, maybe. How does it know if it's doing a good job? That's where this loss function comes in, right? That's the grading system.
You've hit on it, yeah. The loss function basically compares the path the UDE predicts, its estimated trajectory, with the actual path from the observed data. It calculates a score, essentially quantifying how wrong the AI's current guess is. And that score guides the learning process. The AI's goal is always to minimize this loss, to get the lowest possible score, which, ideally, means it's found the true underlying dynamics.
And traditionally, these models use something called mean squared error, or MSE. Sounds pretty straightforward. It measures the squared difference between, the estimated value and the actual value for each variable independently, then averages them out. Seems logical enough, so what's the problem with that? Why doesn't it always work?
Well, this raises a really important point. While MSE works great in many, many cases, it runs into trouble, sometimes serious trouble, with systems undergoing bifurcations. Those are the sudden fundamental changes in behavior we mentioned earlier, the tipping points. So take the Selkov model, for instance. It describes oscillations in glycolysis, which is a core metabolic process. Now, if this system can undergo a hot bifurcation from a stable, steady state to one that oscillates rhythmically, an MSC-trained UDE often just fails. It fails to capture those correct, crucial oscillations.
Right, and the reason why it fails is kind of subtle but really important, isn't it? It's this idea that the MSE loss landscape, the sort of map of possible scores, can have these misleading dips, these black holes of loss.
Exactly. Imagine the AI is trying to find the absolute lowest point in a huge, complex landscape of possible solutions. MSE can sometimes lead it into a small dip, a local minimum, and the AI thinks, okay, I'm done, found the bottom. But it completely misses the true, much deeper valley nearby. The optimization just gets stuck there. It's trapped. And this means the quality of the final model becomes incredibly sensitive to where you start the learning process, the initial guess for the neural network's parameters, which often results in the model getting stuck predicting something completely wrong, like a flat line, a steady state, when the real system is actually supposed to be oscillating.
Okay, so if MSE can lead us down the wrong path into these deceptive black holes, what's the alternative? This paper introduces a different approach, right? The length difference and angle difference, or LDA, loss function.
That's right. The LDA loss is, well, I think it's quite ingenious. It's inspired by looking at the system's dynamics differently, not just as a series of separate points in time, but as a continuous trajectory of vectors, all starting from a common origin in that state space map. So think about it like this. Instead of just tracking where a point is at each moment, LDA looks at its movement. Specifically, it optimizes two things separately: the difference in the length of the state vector, like its distance from the origin, and the difference in its angle, its direction of movement. Both normalized, compare between the estimate and the real data.
Ah, okay. So it's not just comparing the absolute positions point by point. It's also looking at the direction and the magnitude of change over time.
Precisely. And here's the really clever bit. While each part of the LDA, loss on its own, the length part and the angle part, might still have some of those misleading local minima, those traps. The key is that these traps tend to be located in different places in the parameter space for each component. But crucially, the true global minimum, the correct solution, is in the same place for both. So by combining them, often with equal weights like 50-50, or maybe adjusted slightly for specific models like they did for Selkov using 2080, you massively reduce the chance of the AI getting stuck in any one of those false traps. It's like having two different guides helping you avoid dead ends.
That makes a lot of sense. So the effect is a much larger sort of basin of attraction for the correct answer, especially for these really complex neural networks, like widening the mouth of a funnel maybe, making it easier for the solution to find its way to the right spot.
Yeah, that's a good way to think about it. The LDA loss makes the whole training process much more robust, much less sensitive to those initial guesses, which allows the UE to more reliably reconstruct the true picture, the true state space portrait of the system. It seems it can pick up on subtle changes in the trajectories curve much earlier, and that helps guide the solution towards the correct type of dynamics, like oscillations when needed.
Okay, theory sounds good. So how did this new LDA loss function actually perform when they tested it? In the wild across different kinds of real-world bifurcation examples.
Right, they put it through its paces. They tested LDA against the standard MSE on 4 classic models. Each represents a different kind of bifurcation, and they're drawn from different fields: neuroscience, biology, chemistry. First, the saddle node bifurcation, using the Fitzhugh-Nagumo model. This describes how neurons switch between resting and firing states like a basic on-off switch. What they found was, with MSE, quite a few of the training runs ended up predicting the wrong stable state. The trajectory just got stuck off the true path. But LDA, it significantly reduced those failures. That angular component really helped guide the trajectory towards the correct endpoint. It's a big deal for predicting those critical transitions.
Okay, that's one. What else?
Then there was a pitchfork bifurcation, using the Gardner model. This relates to a genetic toggle switch in E. coli, how bacteria can flip between two stable genetic expressions. Similar story here. LDA showed better stability, fewer failures compared to MSE, though maybe the effect wasn't quite as dramatic as with the saddle node. Still, definitely an improvement for understanding these biological switches.
Makes sense. What about the oscillatory one you mentioned?
Ah, yes, the Hoff bifurcation, using that Selkov model for glycolysis. This is where LDA really shone. With MSE, the results are often bimodal, meaning it either worked perfectly or it failed completely, getting stuck in that wrong steady state minimum we talked about, like predicting no oscillation at all. LDA, on the other hand, consistently reproduced the correct oscillations. It seems it allows the model to take these necessary, slightly roundabout paths, these detours in state space, to find the correct oscillating behavior, which is obviously vital for things like biological rhythms.
Wow, okay, so a huge difference there. Any others?
Last one was period doubling, using the Russell model, often used for chemical reactions. This shows transitions from simple oscillations into more complex, even chaotic behavior. Here, honestly, both loss functions struggled a bit with predicting very far into the future, mainly because the training data didn't capture the full, wild excursions of the chaotic system. But even so, LDA still showed slightly better performance on average, especially in capturing the early stages of that complexity increase.
So this really shows that LDA isn't just, a neat theoretical idea. It delivers real measurable advantages across different kinds of crucial system changes. That's pretty compelling.
Absolutely. And they didn't stop there. They also checked how robust the methods were. Like, what happens if the system is really close to the tipping point? Or if you start the training from different initial conditions. And again, they found LDA was much more stable, much less sensitive to these variations. MSE, on the other hand, often showed these abrupt, catastrophic failures depending on the starting point. They also noted that for LDA, sometimes tweaking those weights slightly, the K1 and K2 values for length and angle could optimize results even further, especially for really complex trajectories. It just gives you more control and reliability.
Okay, so UDEs combined with the smarter LDA loss function get us much closer to learning the behavior of those missing system parts, predicting the tipping points more reliably. But you mentioned earlier that the neural network part is still kind of a black box, right? We see what it learned, but not necessarily why in a simple equation form.
That's a really important question, yeah. Can we actually look inside that black box? And the answer is increasingly yes, thanks to another clever algorithm called SInDy. That stands for Sparse Identification of Nonlinear Dynamics. The idea is once you've successfully trained a UDE, hopefully using LDA loss, you can then apply SInDy to the output of that trained UDE. And SInDy's job is to identify the simple algebraic form of those missing terms that the UDE learned.
Whoa, okay, so if I'm getting this right, SInDy basically takes the complex internal knowledge stored in the neural network
Yeah.
and translates it back into something we can actually read and understand, like a regular math equation. That's pretty cool.
Exactly. That's the goal. It essentially sets up the problem as finding the simplest possible equation that fits the learned behavior. It does this by considering a whole library of possible mathematical terms, like x, x squared, sine x, combinations of variables, and figuring out which few terms are most important. This sparsity criterion, focusing on simplicity, isn't just about making the results easier for us humans to interpret and analyze, which is huge in itself. It can also have a practical benefit. Sometimes, by finding that underlying simple equation, SInDy can smooth out tiny numerical wiggles or fluctuations that might still be present in the UDE's neural network output. This can occasionally lead to even better, more stable long-term predictions. It's really a powerful step toward genuine scientific knowledge discovery from data.
So pulling this all together, what does this mean for, for you listening, trying to make sense of complex information? Well, it means we're getting significantly closer to understanding and maybe even predicting those sudden dramatic shifts we see in real-world systems, even when our starting knowledge is incomplete. Think about the potential implications, maybe earlier warnings for climate tipping points or understanding sudden turns in disease progression, things like that.
Yeah, to summarize, this LDA loss function really offers a more stable, more accurate way to get at the long-term dynamics of complex systems, particularly those prone to these bifurcations, these tipping points. It dramatically cuts down the risk of the model just completely failing, getting stuck in those black holes of loss that can plague the traditional MSE approach.
Right. And this deep dive really highlights something fundamental, I think. How paying careful attention to the basic building blocks of machine learning, like choosing the right loss function, can unlock major breakthroughs, especially for understanding these really critical phenomena like ecosystem collapses or market crashes. It's about building that bridge between purely data-driven AI and our physical understanding of the world.
Absolutely. And while, the examples used in this paper are still simplified compared to the full complexity of the real world, the results are really encouraging. They strongly suggest that these complex systems, even ones we don't fully understand yet, can potentially be uncovered using these kinds of methods. It really opens up a fascinating research area, too, where the dynamics of the learning process itself interact in really interesting ways with the dynamics of the system being studied.
So, thinking about all this, what stands out to you, Wee? Where in your own life or work do you see complex systems with potentially missing terms or facing tipping points? And how might a smarter way of, grading an AI's learning process, like this LDA approach, make all the difference in actually uncovering what's going on beneath the surface? That's it for this deep dive. We hope you feel a little more well-informed, maybe a little more curious. Until next time.